Let's do some problems today. So here's problem number 1. So suppose I have a homomorphism of free modules. So let's take R. In this case, let's say R is a commutative ring. Let's take a commutative ring R, and let's take a homomorphism phi from Rn to Rn. Okay, and this n is greater than or equal to 1, and so this is an R module homomorphism. R module homomorphism, and let this be given by a matrix A. Okay, so let this correspond to A, by which we mean, suppose I take EI to be the standard basis element of Rn with all zeros and 1 in one of the places, 1 in the ith place. Then this map phi maps EI to let's call it EJ to summation Aij EI. I goes from 1 to n. Okay, now Aij's are some elements of the ring R, and recall this is how we associate a matrix to a homomorphism. Ij goes from 1 to n. Okay, so the homomorphism phi corresponds to the matrix A, and recall also that we talked about this in the lectures, that this map phi is an isomorphism or an automorphism of Rn is the same as saying that the matrix A here has determinant which is a unit in the ring R. Okay, this was special for commutative rings, and of course the definition of isomorphism is that there is really an inverse map such that the composition is the identity, and this in terms of matrices says that there exists a matrix B, matrices n cross n with entries in R, such that the product A into B is equal to B into A equals the n cross n identity matrix. Okay, so this is just something to recall. Now here's the problem itself. So the question problem says, if phi is an onto map, if phi is onto, show that it is also 1 to 1. Prove that it is also 1 to 1, and hence an automorphism. Okay, so this is the thing that we need to prove. If I have a homomorphism from Rn to Rn which is onto, then it is automatically 1 to 1. Okay, so let's prove this. So recall that, I mean, what does onto mean? So let's draw a picture of this module Rn to Rn. I've got this homomorphism phi, and what I'm given is that it is onto. In particular, it means that if I take these EIs, these basis elements, EI, each EI has, so let's call this element as EI, then each EI has some element of Rn which maps to it under phi. Okay, so there exists an element Xi in Rn which maps to EI under this isomorphism phi. Okay, let's remove this arrow here. So that little element here is EI. Okay, so for each I, we know that there is an element of this module Rn such that phi maps Xi to EI. Okay, that's what surjectivity in particular implies. Now, what that allows us to do is the following. Let's define a map in the reverse direction. Okay, so I'm going to define a homomorphism psi which maps which goes in the opposite direction. Think of it as going the opposite way. Now what it does is the following. It takes each EI to Xi. Okay, remember Xi is somewhat arbitrary here. There may be many different elements of Rn which map to EI. I pick any one pre-image, okay, call it Xi, and I claim I can use those Xi's to define a map psi. Okay, so define R module homomorphism or R homomorphism psi from Rn to Rn by the following recipe by prescribing its values on the EI. So, recall, if I tell you what a homomorphism does to EI, then it is uniquely determined. In this case, I want the EIs to map to Xi. Okay, and that now defines a homomorphism uniquely. Now, what is the property of psi with respect to phi? Well, observe, by construction, if you first apply psi and then you apply phi on any of the EIs, what you get back is EI again. Okay, so it maps each basis element back to itself. Therefore, the composition phi psi is nothing but the identity map. Okay, let me call it I. It's the identity homomorphism of Rn. Okay. So now let's take this. Let's do this in terms of matrices. Let B denote the matrix of psi. Okay, just like we had A, which denoted. So recall, A already denotes the matrix of phi. Okay. Now, what do we know? The composition of phi and psi, and remember R is commutative, so the opposite ring here is the same as the original. So recall, this was our key observation. If I am looking at endomorphisms of Rn, then to each endomorphism I can associate a matrix, but I should really think of the matrix entries as coming from R-op, the opposite ring, rather than the original. If I do this, then these two spaces are isomorphic as rings. Okay. In other words, composition of endomorphisms maps to multiplication of matrices. Okay, and that is where that multiplication involved the opposite map. But now here we are in the commutative ring case where everything is nice. So we don't need to worry about this op business. In this case, R op is the same as R. So now what do we know? Because phi and psi, so the matrix of phi psi, so let me use this notation for the matrix of phi psi, is nothing but the product of the matrices, okay, of phi and psi, which is A and B. Okay, so the matrix is just AB, and on the other hand, phi psi is the identity homomorphism, whose matrix is the identity, the n cross n identity matrix. Okay, so what does that mean? It implies therefore that the matrix A times the matrix B is the identity matrix, and therefore if you take determinants on both sides and recall determinant of AB is determinant of A, determinant of B, even though they have, this is true for all matrices with entries in any commutative ring. This is just the determinant of the right hand side, the determinant of the identity is 1. So what this therefore gets us is the fact that the determinant of A is a unit, because it has an inverse determinant B. And well, what does this mean? This means that phi is an isomorphism. So recall, this automatically means that phi is an isomorphism. In other words, it is also 1-to-1, i.e. it is also 1-to-1. Okay. So onto is enough to ensure 1-to-1 and therefore thereby an isomorphism. So this brings us to the obvious second question: is the same true if I knew that phi was 1-to-1? Okay, could I conclude that phi is onto? So I give you the same question. Phi is a homomorphism, R module homomorphism from Rn to Rn. Phi is 1-to-1. Okay, so the question is, does that imply onto-ness? In other words, is phi an isomorphism? Okay, observe, the same proof will not work anymore, because how did the earlier proof work? We constructed sort of an inverse, a one-sided inverse in some sense, a map in the opposite direction. The same idea will not work here. Okay, so you should try that to see that you can't quite do the same thing, and in fact this statement is false. Okay, so the answer here is no, not quite true. And the examples are very easy to construct. So for example, if I just take R to be the integers, n to be 1, then I am just looking at homomorphisms from Z to Z, and I am asking, if I give you an injective module homomorphism, is it automatically surjective? Okay, and that's of course not true, because here is an example. Each n maps to 2n is an injective module homomorphism of Z to Z. Okay, but of course this is not surjective, because the image is only the set of even numbers. Okay, so that's an interesting thing. If you're given it's onto, then it's automatically 1 to 1. If you're given it's 1 to 1, it's not necessarily onto. Okay, but the important thing here is that all this only holds if R is a commutative ring. Okay, so recall we used the fact that you know that you can talk about determinants and so on, and all of that really only works for commutative rings. Okay, you can't really make sense out of a determinant of a matrix where the entries are from some non-commutative ring, because the determinant involves the expanding the entries in some ways. You have to take products of the various entries, and if you don't quite know what order to take them in, then we are in trouble. Okay, all the nice properties of determinants won't be true anymore. But the question can still be asked over non-commutative ring. So here's my question: is question 1, that is question 1 true over non-commutative rings? Okay, in other words, if I give you a surjective map between from Rn to Rn, does that automatically imply that the map is injective? Okay, and again here we can't use the same proof definitely, because the proof there involved realizing that you can construct an inverse in one direction, and being able to construct an inverse tells you something about the determinant. The determinant is a unit and so on. So we really make very essential use of the determinant there. So well, it turns out the answer is no. Okay, so we really do essentially use the fact that the ring R is commutative, and let's look at several different counterexamples could probably be constructed. So I'm going to describe one of them for you. So here's the counterexample. So let's first look at so I'll tell you what the ring is in just a minute. Before I tell you what the ring is, let me define a vector space. Okay, so let me call this, so it's a vector space of the real numbers. This is I call it R infinity. The elements are just infinite sequences of real numbers. Okay, think of it like this: xi ranging over R, it's just sequences of real numbers, x1, x2, x3 dot dot dot. It's an infinite dimensional vector space. Okay, so it's like an infinite dimensional analog, if you wish, of the finite dimensional vector spaces Rn. Okay, so I think of this as a vector space over R, over the real numbers. And let me define the ring for you. Let's take the ring R. So remember, I'm looking to construct a non-commutative ring. The ring is just the set of all linear operators on this infinite dimensional vector space. Okay, by this I mean it's just all linear maps, T from V to V. It's a linear transformation. T is it's R linear operator. Okay. So the set of all linear operators on a vector space whose dimension is at least 2, this collection of linear operators, they are a ring under composition. It's like if this were a finite dimensional vector space, this would be like the set of all n cross n matrices, where n is the dimension of the vector space. Here it's an infinite dimensional vector space. So you actually have lots and lots of operators, but this ring R is definitely non-commutative. Okay, just like matrices in some sense. And let me sort of demonstrate that explicitly for you. So I will look at two special operators which I will also use for my example. So one of them is called A. It's a following operator. It takes x1, x2 dot 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 and moves everything one step forward. Okay, 0, x1, x2, etc. So this is the forward shift operator, if you wish. It's called the forward shifting operator. It pushes everything one step to the right and puts a 0 in the first place. And there's a backward shift operator which pushes everything one step back. And when it does that, it pops out the x4 blah blah blah, this is a backward shift. Okay, now observe that if I first do the forward shift and then the backward shift on a tuple, an infinite tuple like this, then well, it shifts one step forward and then one step backward. The 0 sort of gets added on first and then removed in the second step. So that's just the identity map, gives me back what I started out with. But if I do it in the other order, then I don't quite get the same answer, because the backward shift will sort of throw the x1 out and the forward shift will put a 0 in its place. So this is like the x1 goes away and I have a 0 in its place. Okay, so observe that these are not in general equal, right? I mean, if x1 is non-zero, they are not going to be equal to each other. So the operator AB is not the same as the operator BA. Okay. Now here's the counter example. So what is it that we want to construct? We wanted to construct a map. So let's review what is it that we are trying to do. We are trying to find, so this R is now this ring of endomorphisms. We are trying to find a surjective homomorphism which is not injective. Okay, so what is it that I want? I want phi to be surjective but not injective. Okay, this can't happen if R is commutative, as we just saw. But if R is non-commutative, in this particular in particular in this example, we will construct such a phi. Okay, so let's do this. So it's in fact enough to take n equals 1. We'll just construct a counter example right there. So look at R, the ring of endomorphisms. Think of it as just a free module over itself. Now let me construct a map phi as follows. The definition is the following: each x in R, each endomorphism of this infinite dimensional vector space, I map it to xa. Okay, A, remember, is the forward shift operator. So each x is mapped to x composition A. Okay, this is my map. This is a R linear homomorphism. So recall that the endomorphisms of R are nothing but the right multiplication operators, right? And that's exactly what's happening here. We are right multiplying by some fixed element of R, okay, the element A in this case. So I claim that this map phi has exactly the properties we want, that it is surjective but not injective. Okay, so let's prove this. So first, why is it surjective? To show it is surjective, let's first look for what element maps to the identity, okay, of this ring R. So observe that if I look at B here, if I apply phi to this backward shift operator B, then that's just going to be BA. Okay, and BA, remember, is just the identity map. Okay, that's the thing that we looked at first. BA is just the identity map. Okay, so in particular that means that if I apply phi to XB, okay, take any x in your ring R, apply phi to XB, then by definition this is XBA, but BA is the identity, so this is X. Okay, so what does that mean? Any element X in your ring here, take any X, it's got a pre-image. Okay, the element XB maps to X, so that means X is in the image of phi, and this is true for every X in my module, okay, in my module R power 1. Therefore, it means that my map phi is a surjection. Okay, let's show it's not an injection. To show it's not an injection, we need to show it's got some kernel, right, that it kills some element. So here's the element it kills. Let me define an operator C as follows. C of x1, x2, etc. is x1, 0, 0, 0. So here's my operator C. Okay, it's sort of the projection onto the first component. Okay, keep x1, make all the others 0. Now observe that, so C is clearly a non-zero operator, right? C is not the 0 operator. Okay, and on the other hand, if I apply phi to C, it gives me CA. Now what is CA? A was the forward shift operator, okay, which is basically it, you know. So when I first apply, let's apply it to an actual element and check. If I apply CA to an element x1 x2 dot dot dot, this is C acting on 0 x1 x2. But what does C do? It keeps the first component as it is and makes all the other components 0. Okay. So in other words, this composition CA maps everybody to 0. Okay. So what does that mean? Phi of C is 0, whereas C itself is a non-zero element of the module. Okay. In other words, the kernel C belongs to the kernel of this homomorphism phi. Therefore, phi is not 1 to 1. Okay. So I hope the example itself is clear. So what this demonstrates is various things, that this surjectivity implies injectivity over commutative rings for free modules. Injectivity does not imply surjectivity even if you are over a commutative ring. And if you are over a non-commutative ring, then you don't get anything. I mean, injectivity doesn't imply surjectivity, surjectivity doesn't imply injectivity, and so on. So this sort of underscores the key role played by this determinant somehow. You know, it over a commutative ring, the fact that you've got this determinant map is very key. Okay, it really helps us in many situations.